Now I am going to explain about inductance and capacitance circuits, then source transformation. Before going into that, a small problem based on the previous explanation. A circuit is given here. See that here it is mentioned the resistors in a parallel circuit are 1 ohm, 3 ohm and 2 ohm, and supply voltage is 6 volt. And what is the total current? So we can circuit also given. So here see that circuit is with 3 resistors, 1, 3, 2 ohm resistors R1, R2, R3 are connected in parallel with a supply of 6 volts. So now to find the total current, how to find the total current? So here we know that based on the previous explanation, one method to solve this problem is find the total resistance. 3 resistors connected in parallel, find the equivalent resistance of the 3 resistors given. So that is given by 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3. So that is calculated 1 by 1 plus 1 by R3 plus 1 by R2 equal to, which gives 1.83. So now R equivalent equal to 1 by 1.83, which gives 0.5644 ohms. So total resistance of the circuit is known. So total current is given by according to Ohm's law. Right? Ohm's law, I equal to V by R. So R equivalent. So V is 6 volts and R equivalent here 0.5644. So 10.98 amperes. So this is one method. Another method also shown here. In a parallel circuit, basically it is explained in the previous class. Total current of the circuit or source current, supply current divides among the all elements in the circuit which are connected in the parallel. So here 3 elements R1, R2, R3. So if we take currents in that are I1, I2, I3, then total current is given by I equal to I1, sum of these 3 currents, I1 plus I2 plus I3. So here we calculate first I1, I2, I3 based on Ohm's law. So I1 is given by, because we know that one more point in parallel circuit, the voltage across each element is same. So that is supply voltage here 6 volts. So I1 equal to 6 by R1, V is 6 by 1, 6, and I2 equal to V by R2, 6 by 3, 2, and I3 is given by V by R3, 6 by 2, that is 3. So total current now it is given by simply the sum of these 3 currents, 6 plus 2 plus 3, which is equal to 11 amperes. So that is a problem, small problem for the more clarity on the previous explanation, series connection of resistors and parallel connection of resistors. Next, inductances in series. When number of inductances in series, what is its equivalence inductance? So here consider two inductors, two inductors. Then here we know that in a series circuit, the same current flows through all the elements which are connected in series. So now 2 inductors L1 and L2 are taken connected in series. Okay, you can see here in the diagram L1, this is L1, this is L2, and they are in series connected across a supply voltage V. Then there is a current I flows in the circuit. So the same current flows through the same 2 elements, and the voltages across each element. Let us take voltage across L1 is V1 and voltage across L2 is V2. So as per the series circuit concept, the total voltage, okay, in the circuit is given by, that is according to KVL, V equal to V1 plus V2. Now, what is V1? What is V2? We know that voltage current relationship in case of an inductor. What is that current voltage current relationship? In case of inductor, V equal to L into dI by dt. V equal to L into dI by dt. Now, accordingly, what is V1? V1 is L1 into, that means with respect to inductor 1, L1 into dI by dt, and V2 is L2 into dI by dt, L2 into dI by dt. So then, and other side, what is V? That is a supply voltage, which is given by L, total L of the circuit, L equivalent of the circuit, total L of the circuit into dI by dt. So on both sides dI by dt gets cancelled. We have the L equivalent here is given by simply the sum of the two inductors L1 and L2. So when inductance is connected in series, its equivalence inductance is given by simply the sum of the all inductances connected in series. Next, inductances in parallel. Inductances in parallel, let us consider here, two or more inductors are said to be in parallel. We know that in a parallel circuit, the basic point is the same voltage appears across each element. In a parallel circuit, same voltage appears across each element. So here two inductors are taken, L1 and L2, which are connected in parallel. So you can see here in the diagram, so which are connected across a supply voltage V, then there is a supply current of I flows in the circuit, which is divided among the two elements. Okay, so in a parallel circuit, the current across different, the current flowing through each element is different. So based on that, so current flowing in L1 is I1, current flowing through L2 is I2. So from the circuit using KCL, written as I equal to I1 plus I2. Now, in a case of inductor, we know that from the voltage current relationship, V equal to L into dI by dt, from that I is given as, from this I is written as 1 by L integral of V dt. Now, so that is what here it is showing. So now put that with respect to each element, So I1 is given by 1 by L1 integral of V dt, and I2 is given by, with respect to second inductor, 1 by L2 integral of V dt, and I is given by supply current, right? So 1 by L equivalent into integral of V dt. So if we cancel both sides, integral of V dt, the equivalent expression when two inductors connected in parallel, that is given by 1 by L equivalent equal to 1 by L1 plus 1 by L2. So this is about inductors connected in parallel. So this is similar to resistors connected in parallel. Next we have capacitors. Capacitances in series. So we know that from the same basic knowledge, in a series connection, current flowing through each element, current flowing through all elements is same, but voltage across elements is different. So based on that concept, based on that knowledge, here consider capacitors in series. Two or more capacitors said to be in series if same current flows to them, flows to all of them. Okay, here two capacitors are connected in series. It is shown in the figure, C1 and C2, and connected across a supply voltage V. Then current I flows in the circuit. So which is same for the two capacitors. Okay, C1 and C2. But the voltage across C1 is V1. Let us take, and voltage across C2 is, let us take, V2. Now that's why it is written as, from the KVL, V equal to supply voltage V equal to V1 plus V2. Now from voltage current relationship in case of a capacitor. What is the voltage current relationship in case of a capacitor? V equal to based on Ohm's law. Okay, V equal to, in place of R we have 1 by C, and in place of R we have in place of R we have 1 by C, and in place of I we have integral of I dt. Okay, so that is a voltage current relationship in case of capacitor is given by V equal to 1 by C integral of I dt. Now apply it to with respect to each capacitor. With respect to C1 it is 1 by C1 integral of I dt, and with respect to capacitor C2 it is 1 by C2 integral of I dt. Next, V is given by, V is nothing but in terms of capacitance, total capacitance of the circuit. Okay, let us say C equivalent, 1 by C equivalent integral of I dt. So cancel both sides, integral of I dt. So 1 by C equivalent equal to 1 by C1 plus 1 by C2. So this is the equivalent capacitance when two capacitors C1 and C2 are connected in series. Next, capacitances in parallel. So this is capacitances in parallel. So here see that. So from the same basic knowledge, when in a parallel circuit, the voltage across each element is same, but the current flowing through each element is different. So here two or more capacitors are said to be in parallel if same voltage across each element. So consider two capacitors here shown in the diagram. C1 and C2 are connected in parallel and connected across a current source here that is shown. So whatever the supply current, source current, that is divided among the two capacitors I1 and I2. So then according to, based on KCL, our total current I is given by I1 plus I2. So based on voltage current relationship in case of a capacitor, we know that V equal to 1 by C integral of I dt. So from this current is written as C dV by dt. So the current is given by, based on that, I equal to C into dV by dt. Now write down this current I1, write down the current for capacitor with respect to capacitor 1 and capacitor 2. So I1 is given by C1 into dV by dt, and I2 is given by C2 into dV by dt, and the total current I is given by C equivalent into total capacitance of the circuit. So C equivalent into dV by dt. So on both sides common term, cancel dV by dt. So C equivalent is equal to C1 plus C2. So this is an expression when capacitors are connected in parallel. So so just this is for a simple understanding, showing all expressions at a time. Series elements. That means resistors, n number of resistors connected in series. the total resistance is given by simply the sum R1 plus R2 plus and so on Rn. And then inductances. And inductances connected in series. The total L is given by L1 plus L2 plus and so on Ln. It is similar to resistors connected in series. Next, capacitances. Capacitances connected in series, n number of capacitors. So when n number of capacitors are connected in a series, the total capacitance or equivalent capacitance expression is given by 1 by C total equal to 1 by C1 plus 1 by C2 and so on 1 by Cn. Okay. Now, when number of voltage sources connected in series, so the total voltage is given by simply the sum of the all voltages. Parallel elements. When n number of resistors connected in parallel, the total resistance is given by R total. That is, expression is 1 by R total equal to 1 by R1 plus 1 by R2 plus and so on 1 by Rn. And n number of inductors connected in parallel, the total inductance is given by L total, that is 1 by L total equal to 1 by L1 plus 1 by L2 plus and so on 1 by Ln. Next, capacitors. N number of capacitors connected in parallel, n number, then the total capacitance or equivalent capacitance C total equal to C simply the sum C1 plus C2 plus and so on Cn. So, if we see here, so resistors and inductances have the same expression when they are connected in series and parallel. But for capacitance, that is vice versa. So, here parallel connection R total is given by 1 by R total equal to 1 by R1 plus 1 by R2 and so on 1 by Rn. But C total is simply the sum. So, that is how easily we can remember. Next, we have source transformation. Source transformation, next topic. So, here basically we have, what are the sources we have in an electrical circuit? In an electrical circuit, the sources we have are, there are two sources, okay, voltage source and current source. Voltage source and current source. And also we know that, okay, these are active elements. Okay, these sources we call them as active elements. And here we talk about only independent sources, independent voltage source and independent current source. Okay, now see that here an independent voltage source means what? An independent voltage source means what? An independent voltage source means it maintains a voltage of fixed value. A voltage, it maintains a voltage. It may be a fixed value or alternating value. Means it may be a DC value or AC value, which is not affected by any other quantity in the circuit. Which is not affected by any other quantity in the circuit. That is called independent voltage source. Similarly, independent current source means which maintains a current. It may be a DC current or AC current, which is not affected by any other quantity in the circuit. Which is unaffected by any other quantity in the circuit. Now, there are two independent energy sources. Okay, there are two independent sources we have. One is ideal energy source. Other one is practical energy source. So under ideal voltage source, ideal current source. Under practical similar manner, a practical voltage source and a practical current source. Next, the electrical sources are those, what is meant by source? Basically, electrical sources means they provide active power to the circuit, they supply energy to the circuit, and already I mentioned these two sources the two sources are voltage source and current source. The purpose of voltage source is to provide voltage rather than current, and current source is to provide current rather than voltage. Okay, so then each source is then categorized as ideal or practical source. Now, what is meant by ideal source? What is meant by practical source? Ideal sources are those imaginary electrical sources which provide constant voltage or current to the circuit regardless of the load current. Okay, ideal means, okay, they are imaginary sources. It provides constant voltage or current. Okay, means what the meaning is, the ideal sources, because see that the ideal sources do not have any internal resistance, but practically speaking, every source has it is designed with some internal resistance. That's why it is mentioned as imaginary electrical sources. Ideal sources are imaginary sources, okay, which provide constant voltage or current irrespective of the load, whatever may be the load, it is connected at the load place. Okay, that means the load here, based on the load may be a resistive load or inductive load or capacitive load. The load means the consumer. Okay, see that we know whatever uh, the people who are consuming the load, who is consuming power, is called load basically, right? So in a in electrical circuit, there is a source, and there are elements, number of elements, and at the output, okay, there are elements, number of elements. This is called output terminals. Usually they denote that output terminals are load terminals also, they say it as. So at this place usually the load is connected. This is load. So it may be a resistor, it may be an inductor, it may be a capacitor. So practically speaking, load means whatever it is consuming power from the supply source, from the source. So here practically, generally speaking, that is consumer. Load means consumer. Uh, Consumer means we are domestic consumer. Like that, there are industrial consumer, agricultural consumer, who all consumes power from the source. So see that here, coming to our topic. So ideal source means, okay, which provides constant voltage or current. Okay, if it is a voltage source, it provides constant voltage. Okay, so, and current source, regardless of the load, whatever may be the load, it may be a small consumer like domestic consumer, it may be an industrial consumer like it comes under big consumer, whatever may be the consumer, it supplies constant voltage or current. Now, the ideal sources do not have any internal resistance. So that is called ideal source. Where it is impossible to build a source with zero internal resistance. So all the real sources are practical sources. So It is impossible to build a source without internal resistance. Okay, that's why all real sources are practical sources. Next, so these are the characteristics. These are the characteristics of voltage source and current source. So first is about ideal voltage source. This is practical current source. Sorry, practical voltage source. So see that an ideal voltage source, how it is shown, a small circle, or we can also show it is actually DC. It comes under DC voltage source symbol. We can also show the same with the two lines like this, plus minus V. So ideal voltage source, okay, across its load terminals, okay, these are its output load terminals. So we know that ideal source means whatever may be the load here, okay, so which draws current, right? So what if you take current on x-axis, that voltage magnitude on y-axis, it maintains constant voltage irrespective of the load current. Okay, if you, even though your load goes on increasing, but it supplies constant voltage. So that is ideal voltage source. Next, practical voltage source. So means we know that there is a internal resistance present with the voltage source. That resistance is shown with small r here. So what happens when load is connected here? When load is connected here, so when current flows, when current flowing, so what happens if we go on increase this load, the current drawn by the drawn from the supply also increases. So there is a increase in the voltage drop across this internal resistance also. So what happens, automatically the magnitude of this V goes on decreasing. That's why if we see the VI characteristics, if we go on increase the current, the magnitude of this V, it slowly falls down. Okay, so that is why the curve shown like this. Next, ideal current source, and this is practical current source. Now, so current source, okay, this is a symbol of a current source. Inside a small circle, an arrow is shown. So arrow shown upward means current flowing in this direction, upward direction. Okay, and AB, terminals AB are the load terminals. So see that, so whatever may be the load here, it maintains. So in VI voltage current characteristics, current is taken on y-axis, voltage is on x-axis. Whatever may be the load, current, it maintains a constant current. That's why it is shown constant. Coming to the practical current source, it has a resistance. Okay, know that current source has its internal resistance connected in parallel with it. Okay, now if a load is connected here and go on increase the load, the current drawn by the load increases, and okay, and similarly the current drawn from the supply also increases. That's why there is a less in the magnitude of the current source. That's why there is it slowly falls down if you go on increase the load. Okay, if you look at the voltage current characteristics. Next, Okay, next is we have source transformation, means transforming a given voltage source to current source and vice versa. Converting a given voltage source into a current source and vice versa. So here a voltage source given, okay, practical voltage source with magnitude Es and its internal resistance Rs and a load resistance across its load terminals. Okay, these two dots represents the load terminals. RL, load resistance is RL. So, and across that the voltage is shown as VL, and then current flowing in the circuit also shown as IL. Now converting this given voltage source into a current source. How to get this current source, equivalent current source? In the current source equivalent circuit, we know that there is a current source with a parallel resistance. So to find the magnitude of this current source, okay, which is given by the voltage source magnitude E over Rs. Okay, E magnitude divided by its internal resistance gives the current source magnitude. So E by Rs. Next, it is parallel resistance value is same as the internal resistance of the voltage source, and load resistance also keeping as it is. Okay, and vice versa. Suppose if a current source is given like this and get the voltage source, its equivalent voltage source circuit. How to get this E is given by that current source I multiplied with its internal resistance I into Rs, and its series resistance is same as the parallel resistance of the current source. So a small example is shown for an understanding here. Determine the equivalent constant current source for a voltage source with open circuit voltage of 120 volts and internal resistance of 6 ohm. So that is shown here. Okay, so 120 volts voltage and its internal resistance 6, and then its resistance is calculated by, we know that from Ohm's law, 120 into 6. So which gives how much? Which gives, it's sorry, from Ohm's law 120 by 6. So it gives 20 amperes. 20 amperes, and its resistance is same as internal resistance of voltage source. Next, one more. Determine the equivalent constant voltage source for a current source with a constant current of 40 amp and internal resistance of 0.8. So here current source is given, they are asking its equivalent voltage source. So current source value is 40 amperes. Okay, so its equivalent voltage is given by from Ohm's law, V equal to IR. So 40 into 0.8, right? 32 volts. Look at the polarities of voltage source. Okay, and resistance is same as the current source resistance only. Now look at the direction polarities. So here current source direction is polarity is shown downward. Okay, it is shown downward, means it's that means we know that basically current always flows from high potential point to lower potential point. So based on that, the voltage source magnitude also shown similarly the same way. Okay, if the current source is if the voltage source is like this, that means current flowing upward. That means it starts to flow from higher potential point. In a similar manner, if the voltage source magnitude is like this, means current polarity is shown like this. So based on that knowledge, so the voltage source magnitude here it is shown, it is plus, it is minus. Okay, that's all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.